Good morning, everybody. I hope you are doing well today and ready to wrap up our discussion on fractions. Now, I understand that the connection again seems to be less than ideal. I don't know why. I don't know why the connection isn't good. It's always been okay this semester. So I apologize if I cut out. If you need me to repeat something, just let me know. Other than that, there's not much we can do. All right. Now, what I wanted to do today is give you an idea of how things look in reality, sort of behind the scenes. Even though at an elementary school level, we don't necessarily see the whole picture. When it comes to fractions, we see uh, some diagrams, we make some lines, we draw some pictures, we can get an answer, and maybe we can do some shortcuts in the later grades to calculate with fractions a little bit more effectively. But there's much more happening here. So I wanted to give you a taste and a preview, and maybe you're interested, maybe you're not. These things will not be on the written quiz, but they can be in the oral test if you still have to do something like that. Okay, so what do we have? Let's take a step back before fractions. We actually didn't have a number line when you think about it. Now I'll draw the number line simply because apparently I need to practice. But when you think about it, we didn't actually have a number line when we only looked at the integers. The integers, this collection or the set of integers were given the symbol Z with a little extra line to make it fancy. But what we really had were just a bunch of dots, right? We had positive integers, and they went on forever. We had 0. We introduced negative integers. Well, people did, not me personally, because we had to represent the idea of debt, of owing someone something. So there were these other integers. And mathematically speaking, there's an additive inverse of every integer uh, added together to cancel its effect. So the integers came about, maybe not as rapidly as I would think, but it makes total sense when we look at them that there has to be a negative counterpart to every positive integer. Okay, so we have the integers uh, pretty early on. And then, of course, it didn't take long to for someone to realize, well, I have a full loaf of bread. If I cut it in half, how do I represent what I give you? If I only give you a portion of a whole one loaf of bread. So there were obviously these other numbers, fractions, littered all over the place. Maybe 1 1/4. Now, whether you represent it with a mixed number, whether you represent it with an improper fraction, whether you represent it with a decimal, it really doesn't matter. The point is that these guys exist, scattered throughout in between these existing integers at the time. So the fractions, so if I notice here that an integer like 2 is also a part of the fraction family because any fraction, any one of this larger family can be represented with a numerator and denominator. So much as extended the collection of numbers that I have. This larger family they called the rational numbers, and they gave the symbol Q with a little line. So That's anything that looks like A over B with A and B both integers. Now, I don't really mind if you don't understand the set builder notation. It's okay. Remember, I'm giving you a preview for how things are written, are explained, are discussed, how they look, pulling back the curtain just a little bit. And perhaps that sparks your interest. You never know. Because when it comes to number theory, there is really no end to this topic. Okay, so we've extended this to what we call the rational numbers. Now, this this collection is what we call closed. It's sort of self-containing. Self-containing. In that if we take any, I'll call them A and B again, A and B in this set of rational numbers. If I take any one of these on the number line, could be a little fraction, could be a nice whole number, doesn't matter. Then I'll just write it informally here to not bother people too much. Then if I add them, actually I'll write it like this. Get away from me, little line. There we go. Then if I add them, if I subtract them, if I multiply them, if I divide them, they're all still answers that are rational numbers. You can do that by example to just convince yourself. Take any one of these, any fraction, anything. If I do a calculation with them, then the answer that I get is still going to be a fraction or a ration or an integer, a rational number. So we don't take some of these and then jump out of it. It's self-contained. It's closed. Okay. More than that, there's another property. Now, this, if you know a little bit more, this is, I'm not defining density on purpose. It's dense in the sense that on this number line now, there are no gaps. If I take any two, let's suppose there's my A, and very close next to it is another rational number, B. Then there will always, for any two of these that you take, there will always be another rational number in between those two. Then you can take those two. In between those two, there's another one. So any gap that you look at, regardless of how tight they are together, there's another rational number in between. And of course, that's not true for the integers, right? There's no integer between 2 and 3. There's a huge gap between them. But we draw a line because when it comes to the rational numbers, they have this density to them. Take any A and B rational numbers, then there exists, let's call it Q, rational number, in between A and B. And it's really quite simple. We just need an example, right? There are actually many. Q, just make it the average of the two, A plus B over 2. Because I've added and divided with rational numbers, that answer is necessarily also a rational number. Oops. Yet it sits between, A is on the left side of it, B is on the right side of it. It sits strictly between the two. It's a that sits in the middle. And I can do that for any two rational numbers you can come up with. You can make them super tight. You can make them 1 over a million and 1 over a million and one. There's going to be another rational number in between those two. So I have this density, which is why we draw the number line, because there are no gaps in between for empty space. They are dense. So I get, even though I have infinitely many integers, of course, right? 1, 2, 3, 4, 5, it goes on forever. I can count them off everything. I obviously also have infinitely many rational numbers. And it does seem as if there are more of them. But that's a topic I don't want to get into right now. There actually are exactly the same amount of them, even though it seems okay. So when the Greeks were mainly the culture that started this exploration, so I'm going to check if I have comments on YouTube. I didn't open that window. The Greeks were mainly the ones that started this discussion or exploration from an abstract point of view, not a practical application point of view. Come on, just open the window. This is so slow today. Sorry, I just wanted to check if there's a YouTube comment as well. Anyway, and they were pretty happy with themselves for discovering these properties of rational numbers. Fractions were obvious. There's a lot of connections with music and harmonics and all kinds of things. So they were pretty patting themselves on the back, pretty happy about their discovery and their accomplishments and the properties that they realize about rational numbers. And in true human arrogance, I guess, they were convinced that, look, these are dense. There's no gaps between them. We found all numbers. Good job. Pack it up. We can go home. We figured this out. The rational numbers, fractions, that's it. We've done it. Perfect. Good job, people. And for quite a while, they were quite pleased with themselves. And everyone believed it. Everyone was happy. At the same time, a little before, I guess, a very well-known figure, Pythagoras, proved something else about triangles that everyone probably knows. Try and make a pretty triangle here. There we go. In a right angle triangle, if one side length of the perpendicular sides have length A, the other side of length B, and then the hypotenuse can be measured, C, there's always a relationship a squared plus b squared equals c squared. Now, proving this isn't too hard, and there are many different proofs of this. That's not what I want to focus on. This was also known, believed. There are like hundreds of proofs of this. No one doubts that this is true. Great. So now, when you take a piece of rope, let's suppose I take a 1 unit long piece of rope and I lay it on the ground. 1. Whatever your unit is, meters, feet, whatever, I don't know, doesn't matter, I don't care. And I take another piece of rope, also length 1, and I lay them at a 90-degree angle. Then I have some extra rope, I lay it across here, meeting these endpoints, of course straight. Let's call that length C, and I cut them off, boop, boop, cut it off. I have now constructed a length of rope. That therefore this length has to be representable with a number on this number line. I'll call it C because I don't know what it is. So if I look at Pythagoras and the identity, the relationship between all these lengths, of course, it's a right angle triangle, so this has to be true. I can calculate, well, I can't calculate C. I know it exists, but I can represent it with a new symbol in a way. 1 plus 1 is 2, of course, and we call that symbol square root of 2. Simply so that I don't write c squared equals 2, it's just another version of the exact same information. And up to that point, we didn't really know what that number looked like, so we call it the square root. Okay? It doesn't really matter what we call it. I can call it Bob. The point is, it exists. It exists. I measured it. It's there. I have a length of rope of length root 2. Now the pickle is that at this stage, we're convinced, as Greeks, we're convinced that all quantities, all numbers are fractions somewhere on this number line. They are there. I just might not be able to find them. I might have to give them another name, but it's there somewhere. Where is this guy? Remember, they don't have any calculators or anything, right? So they were convinced that this number has to be somewhere on this number line. Yet, regardless of how much they try, they can't find it. They cannot find exactly where this quantity sits. What is the fraction that is equal to this quantity? What is A over B? What is the numerator? What is the denominator? So that it equals the square root of 2. Can't find it. But they religiously believe that everything is on this number line, yet they can't find this one. Then one of Pythagoras' students came up with a little argument. Well, let's just suppose it is, there is an a and a b, such that we have the fraction. Our goal is now to find what is a and a b. And because it's a fraction, let's just take the a and the b fraction in simplest form. So it's simplified as much as I can. There's a fraction, I just don't know what it is, right? But we all believe that it's there. So let's just go ahead and call it a and b. Then if I rewrite this a little bit, by multiplying with b on both sides, I get a equals square root of 2 times b. Right? I'm multiplying with b on both sides. So if I then square both sides to get rid of the square root, I get a squared equals 2 times b squared. Okay, so let's just put a box around that guy. This means that the number a squared is 2 times something. That means a squared is even. So 2 divides into a squared. It's an even number. It's 2 times something. Now, I don't care about the something right now. This number is divisible by 2. A squared is divisible by 2 because I can write it as 2 times something with no remainder. Okay, good. Now, a little bit of extra properties here that we've never really discussed, that because 2 is a prime number, I can't split it up and because this is a times a, right? I can't split it up and some of it can go into the first a, some of it can go into the other a. It's a prime number, doesn't work like that. The only way that this can happen is that the 2 goes straight into a single a. So a is divisible by 2. Now there's a property that allows me to do that. We didn't prove that, but it's when you think about building blocks, it's not that big of a stretch. So a is an even number. So let's write, so any even number you can write as 2 times something. Now I'm not going to do it like this. This was for a squared. I'm just going to write 2 times k for some k. This is pretty standard stuff for some integer k. Oopsie, don't do that. Pretty standard stuff. Now let's go back into the box. So if I then insert what the new version of A is into this, I get 2k everything squared equals 2b squared. Now I know this is a little bit advanced, but we're peeking behind the curtain now, so I want to give you a taste. So if I square, I get 4k squared equals 2b squared. If I divide both sides by 2, I get 2k squared equals b squared, or the other way around. This means that b squared is also divisible by 2, which means that b is divisible by 2 for the same reason. So let me just zoom out here. We said that a is divisible by 2, and now b is also divisible by 2. I'll put it over here. That means the fraction a over b is not in simplest form, because I can cancel a 2 for both. Yet my original assumption was that it is. So I'm sort of stuck in a loop here, that if I take square root of 2 as a fraction in simplest form, I have a common factor that I should cancel. If I then cancel that, it's then in simplest form, and it's going to happen again. It's going to happen again. It's never in simplest form, because there is no such fraction. So this is a contradiction, maybe a little stranger of a contradiction than I'm used to with my logical reasoning, but it is nonetheless. My conclusion is that this cannot happen. There is no fraction. It doesn't exist. No fraction that could equal exactly square root of 2. No fraction exists like a over b that equals square root of 2, which means square root of 2 is not in this collection of rational numbers. Yet it is a number. It's not on here. It's not on this number line. It's not a fraction. Now, this was such a revolutionary thought at the time that the school of Pythagoras, which is the group of followers of Pythagoras, when one of their students called Hippasus discovered this, it's logically sound, 100% confident, that it was such a revolutionary thought that they couldn't let it get out because it would completely shake all their beliefs about number systems. And the only way to ensure that this information didn't get out was to kill him. So they took him to the river and they drowned him to try and contain this information because it was that groundbreaking. But of course, truth is truth. Eventually it's going to come out, and it did, because there is no denying that square root of 2 is not a rational number, yet it exists. So we get these, there's other numbers here. And they are called the irrational numbers. Not because they're crazy, just because they're not rational. Now, I don't like the symbol, but it's an I with an extra line. It's not a Roman number, but it is easily confused with a Roman number. Irrational numbers. Let me redraw the number line. We can create those lengths, so those numbers are there, but they are not fractions. They're something else. And they are scattered everywhere. So square root of 2 sits over here. I think it's 1.4 something. These irrational numbers are, if you think in decimals, the non-repeating non-terminating decimals. Fractions come from or correspond decimals, obviously, also fractions, also rational numbers. But there's another kind of decimal number, the one that never repeats and never stops. There is no pattern that ever repeats among the decimal digits, and it never stops. Those are irrational numbers. No fraction representation is possible. Now, there are infinitely many of these. Infinitely many. Actually, uh, I can't really explain this for our level, but there are infinitely more of these irrational numbers than there are rational numbers. If you could somehow count all the fractions, all the rational numbers, count them, make a list. You can do it. Systematically tick them off. You'll never stop, but you can make that list. It is impossible to do for the irrational numbers. There are infinitely many times more of them. So if I take square root of 2, for example, and of course I can take any one of them, then and take some rational numbers. Oh, sorry, I keep drawing the element symbol, which you don't know. Take some rational numbers. Then if I do a calculation by multiplying and adding, then that is also an irrational number. So as soon as I have an irrational number, a calculation with with fractions mixed in with that number, the answer is also going to be an irrational number. I don't get out of the irrational numbers. I just create more irrational numbers. So they're scattered, more of them, infinitely many more, just creates more irrational numbers. Now, that's not really the reason for infinitely many times more. That argument is a little bit fancier, but it's so hard to believe. There are different levels of infinity. There are different levels of infinity. How many integers are there? Infinitely many. How many fractions are there? Infinitely many. There are also infinitely many irrational numbers, but there are way more of them than there are the integers, for example. How many times more? Infinity times more. That's how many. Yet, what makes it even more freaky is that the rational numbers were as dense as I could imagine them. Between any two, there's another fraction in there. There is no space. Yet, infinitely many of these other numbers are squeezed in here somewhere. And the more you think about it, the more it messes with your head a little bit. And that, well, I mean, it's reasonable to expect that these irrational numbers are dense as well. What do I mean by that? Let's take now there are many versions that let's write it like this, between any let's say a and b rational numbers, there exists what shall I call it? Let's say an irrational number. Now, there's probably a lot more of them, but I just want to know there is one. So just like for the rational numbers that take any two, there's another fraction in between. Maybe know that there is one. What would this look like? And we'll end with this. It's a little bit more complicated. Let's start with the fact that 1 over root 2 is also an irrational number. It kind of has to be. Otherwise, root 2 isn't. if I assume that this is a fraction, that would mean root 2 is a fraction, and we know it's not. It is an irrational number. So when I flip it, it has to be as well. So I take an a and a b. Well, sorry, no, I don't take an a and a b. Uh, if I noticed how much this is like 0.7 something, I think. So it sits nicely between 0 and 1. Sits nicely between 0 and 1. Okay. I want to eventually find an irrational number that sits between a and b. Just giving you a taste of how this argument could go. So what I'm going to do is I'm going to multiply the whole between a and b. Now, with inequalities, if you remember your high school stuff, I can multiply throughout as long as this is positive. It doesn't change the inequality sign. Now, 0 times anything is 0. Then I have this 1 over root 2 times b minus a. And 1 times anything is just that thing, b minus a. And then I'm going to add a everywhere. 0 plus a. I just add, so I don't change the inequality sign. A plus this guy. And a cancels with this a, so I just have a b. So I have something that's squeezed between a and b. And because this is we call it a linear combination, a calculation involving an irrational number, this is an irrational number. Irrational. So between any two rational numbers, there's just another irrational number. Actually, many more. And between any irrational numbers, there sit more irrational numbers, but that one's a little bit messier. If we prove something logically with deductive reasoning, then the truth has to come out. It's just unfortunate that people had to die to sort of as in reaction to something that at the time was quite revolutionary. So hopefully with this, you get to peek a little bit behind the curtain and see what's actually happening here with numbers. A lot, a lot is happening. And at an elementary school level, we barely get a glimpse of it. There's a much, much bigger world that some people are interested in and some people are not. Of course, everyone is different. But maybe this sparks your interests. Maybe you want to explore it further. Maybe you're good to just know, oh, things are more complicated. I'm glad I don't have to do that. Whatever side you are on, it's good to sometimes just see a little bit more than what we currently know. That is the end for me today. Are there any questions or comments on this? I know, speechless. It's quite disturbing to me when the more I think about it, the more disturbing it gets that there's no space between rational numbers, yet somewhere infinitely many other numbers are sitting. Where are they sitting? I don't know. And we don't know a lot of irrational numbers. Square root of a prime number is the easiest ones. Numbers like pi, things like that, are all irrational. But there are infinitely many more. Think of all the fractions you know. If you had to make a list of fractions, you can do it, and you would probably never stop. You know so many fractions. Yet there aren't 10 times more of that, not 100 times more, not a million times more. There are infinitely many more irrational numbers that are somehow squeezed on this line. It's weird, but also very interesting. All right. Clearly, there are no questions. Then we will end our discussion here. Tomorrow, I believe, is a catch-up day, Q&A. If you have any Qs, bring them by. Otherwise, we will move on to our next chapter soon enough. Until then.